Okay, hello everyone, welcome. uh, um, uh, Regarding the grades, I was talking about like thinking of slightly modifying um, the grading scale a little bit. Because I came to know that you guys have to pass with C to continue. But anyway, you're in the final year. But I'm thinking of slightly modifying the grading scale to help you get C or above. Okay, so I will let you know next time. Okay. Um, Today we're going to start a new topic, which is the last topic. Before we start, do you have any question, anything about the previous topic or previous chapter? Okay, let me share the screen first. Okay, so today's topic is about oscillators. We have finished the topic, some points about the active filters, how to design active filters using different circuits. Today we are going to start talking about how to design an oscillator, okay? And the outline of this lecture is going to be an introduction about different types of oscillators, uh, sinusoidal oscillators or non-sinusoidal oscillators and their different types. We will focus this in this lecture only on sinusoidal oscillators, and we will study two of them, the Vine bridge or Venn bridge circuit, and the second one is phase shift oscillator. Okay, so the goal of today's lecture is to understand the idea of sinusoidal oscillator, how we create a sinusoidal oscillator, and we will study an implementation using these two circuits, the Venn bridge, which is a very popular implementation or circuit, and the phase shift oscillator. Okay. So what is an oscillator? An oscillator is an electronic circuit, okay, that generates a periodic waveform. So if you need to generate a periodic waveform that repeats itself every period t with a certain frequency, whether you're talking about sinusoidal signal or non-sinusoidal signal. So you might have a sine wave, okay, so you might have a sine wave. Okay, you might have a rectangular wave or square wave. You might have a triangular or sawtooth wave. So it's a periodic signal. Okay. Sometimes we refer to the oscillators as multi-vibrators or waveform generators. Okay. So these are alternative names of the same thing, which is the oscillator. You can classify oscillators broadly in these two categories. You have a sinusoidal oscillator. So in this case, you have a sine wave. The output is a sine wave, pure sine wave. And non-sinusoidal, mainly rectangular or square wave, and maybe triangular waveform, okay? So, and of course, you can also generate this one, and from this one, you can generate a sine wave as well. Sinusoidal oscillators, they are mainly RC circuits, LC circuits, or crystal oscillators, okay? In this lecture, we are going to focus only on this part, okay? So the whole lecture today, we're going to spend it on the RC oscillators, RC circuits to build a sinusoidal oscillator. Later on, we'll cover this one, and maybe we'll move to this one after that, okay? Non-sinusoidal oscillators, they have an alternative name of relaxation oscillators. We call them sometimes relaxation oscillators. They can be classified into bistable, monostable, and astable. Okay. The sinusoidal oscillators, they have the idea of, they are built around the idea of having a positive feedback. So you make a positive feedback using an amplifier and a feedback circuit, which is most likely a filter, and using this configuration to create a sine wave. The non-sinusoidal oscillators, they are based on the idea of a capacitor. You have somewhere a capacitor in the circuit, and you start charging, discharging the capacitor, okay? Charging, discharging, charging, discharging. So they are based on a timing circuit. You have a timing circuit, an R and C, and this timing circuit is used to charge and discharge the capacitor in some rates. Then this will generate a certain type of a waveform, okay? And bistable means you have two states of stability. You have two stable states, okay? So you have two stable states, and here you have one stable state. Two stable states similar to a switch. If you have an on-off switch, this is a bistable. Or if you have a flip-flop, okay? So flip-flop needs a trigger, and we can set or reset the output to a 0 or 1. So it has two states, okay? So this has two states, and this one has a 1 state, okay? So this is similar to a switch, a lamp switch in your home, like when you turn the switch on or off. So you have to keep it in one of the two states. But the monostable, on the other side, the analogy of it is the button, the push button of your doorbell. Like if you have a doorbell push button, okay, so you have a push button like this, and it's always in the off state unless you press it momentarily, like for a few seconds, to turn it on, and then it goes back off. It goes to off state again. So this is called the monostable. So definitely these are not sinusoidal. These are not oscillators. They create either a pulse in the two states, or just a small pulse, or they can alternate between the two states here, or they can generate just a pulse with certain duration. Okay, so they are not like explicitly an oscillator that will remain forever. But the astable is the one that will create a function, a waveform that will go forever. Okay. So this is how we understand or classify oscillators. Okay. So this is, as I mentioned, we have two types of oscillators: sinusoidal oscillators, and this is what we are going to cover today. Okay, so these are the sinusoidal oscillators, and they are based on the unity gain closed loop method, and we're going to discuss this method today. And they are classified further into RC circuits, and these RC circuits are used because mainly you use an amplifier, and this amplifier is mainly operational amplifier. And we know that the operational amplifier has a certain bandwidth, small bandwidth, maybe 1 megahertz, 2 gigahertz, 2 megahertz. So the output frequency is in a few kilohertz, maximum 1 megahertz or 2 megahertz maximum. While in the other side, so the application for this, you can use them in application in low frequency application, no more than megahertz. But if you'd like to go to the RF circuits with where you work up to gigahertz and these high frequencies, then you have to opt for an LC circuit. Okay, so the oscillation here is done through a transistor maybe, and an inductance and capacitance. So the frequency ranges from 100 kilohertz roughly up to maybe 1 gigahertz or above. The third category of the sinusoidal oscillators are the crystal oscillators, and crystal oscillators are made of some crystals that when you apply a certain voltage, they will oscillate. Okay, they create a vibration, and these are common in computers and microprocessors. When you see like something like this in the board, that has a frequency here, sometimes 20 megahertz or 20 kilohertz. These are crystal oscillators, like metal component like this in your computer or in your microcontroller. These are crystal oscillators. They are very precise in their output frequency, and they have frequencies ranges from 10 kilohertz, few kilohertz, up to few megahertz or tens of megahertz. The second category is the non-sinusoidal oscillators, and sometimes, as I mentioned, we call them the relaxation oscillators. These types of oscillators, they use the timing method, a capacitor that has been put in charging and discharging. So you charge it, discharge it, charge it, discharge it to create the output signal. And as I mentioned, they are classified further into bistable. You have two states, like the flip-flop, monostable, one state, like the push-button switch, astable, that has no stable state. It keeps oscillating between the two states forever. And an example of this is the 555 multivibrator. This is a chip, an 8-pin chip, similar to the 741. It's a chip, okay, like this. It's called LM555, and it has 4 pins, similar to the 741 operation amplifier, but this is not an operation amplifier. This is an oscillator or a function generator. You can use it to generate square waves with different duty cycles. You can create a triangular circuit and so on, okay? A triangular waveform and so on. So these are the classes of different oscillators. And the first one we're going to begin studying today is the sinusoidal oscillator, okay? So sinusoidal oscillators, how they work and how to analyze them and how to find the conditions for them to oscillate. So sinusoidal oscillators are basically, they consist of two parts. The first one is an amplifier. So this is an amplifier, most likely is an operation amplifier that provides a gain, K, okay? We call them A of S, okay? And a feedback network, and most likely this is a filter, okay? So this is a filter, and we call it beta or B of S, okay? So we have we have a feedback loop, and this feedback here is a positive feedback. So unlike the negative feedback techniques that we learned a few weeks ago, in this case, this is a positive feedback. And remember, at that time, we said we don't use positive feedback in creating amplifiers. But in this case, we are not creating an amplifier, we're creating an oscillator. So we have to have a positive feedback. And positive feedback creates either oscillators or comparators, or saturated output. So we have two components, amplifier and a filter in the feedback, and a positive feedback, okay? And if you do the analysis, as we're gonna see, then this is the transfer function of this system here. If you divide, so this is X output of S divided by X input of S, okay? So if you, or X source in this case, okay? So this is S. You can analyze this, as we're going to see now, by defining a signal here, and then you find the overall transfer function. As we mentioned before, if you remember, we always call this amount as the loop gain, okay? So A of S times B of S. So in general, these two functions or two blocks are function of frequency. So they are A of S, B of S, and if you substitute S with J omega, you will have A of J omega times B of J omega. So they are function of frequency. So the loop gain is A of S times B of S, and 1 minus A of S, B of S, we call it the characteristic equation, okay, when you equate this with 0. Well, an oscillator is a function generator, is a circuit that generates an output without an input, okay? So actually, we shouldn't have this input here, okay? If this is an oscillator, the circuit will build up by itself and generate an output, sine wave output, without even having an input. But here, just to for the sake of analysis, we have added an input. Later on, we can assume that this input is 0, and we'll see that the circuit will work by itself and generate the output, okay? The network portion here, the frequency selective network beta of S, is the principal portion of the loop that is dependent on frequency. So K normally is independent of frequency, or A of S is a constant. So A of S is not a frequency dependent, but B of S is a function of frequency, okay? So it's a function of S, and then therefore it's a function of frequency. Okay, let's go ahead and see how to analyze this circuit as we did in the negative feedback. So we define this as VF, V feedback, okay, and this is VN, okay. So we see that V output is AS, okay, this gain times this signal here, and the signal here is V input plus V feedback, okay. So you multiply this by AS to get a V out, and you find that VF actually is V out here multiplied by this block here, the positive feedback block. So you can substitute this here. So A of S times VI plus, and you substitute VF with B of S times V out. And then you rearrange, making the output, the V output in one side. So you send this term here to the other side. You get 1 minus AB times V out. And the gain, which is V out over V in, is going to be A over A 1 minus A times B. Okay. If at any point we make 1 minus AB equals 0, then this gain is going to be infinity. Okay, and this is the idea of oscillation, is to make the denominator here equals 0. Once the denominator is 0, so that means AB equals 1. So if AB equals 1, then this denominator is 0, and the whole transfer function is infinity. And in this case, the circuit will have an output even if V input is 0, because the gain here, the loop gain, is infinity, right? Or the loop gain is 1, sorry, the loop gain is 1, and the overall gain is infinity. Okay, the overall gain is infinity. So if the overall gain is infinity, then the circuit will generate an output without even having an input. Okay, and you might ask how this output builds up. Actually, it starts from any component in the circuit due to thermal noise. So any component, any resistor, any conductors in the circuit will have a certain thermal noise, like it generates some voltage due to the temperature, and this voltage will build up, continue building up until the output builds up, and you will have an oscillation. Okay, so it's due to any thermal noise inside the circuit will create the output. And of course, these circuits are not passive circuits. They have to be connected to a bias voltage VCC or VDD and so on. So they are connected to a DC, and this DC will create the amplification process. Okay. Any questions so far? Okay, so what are the conditions? So if you have a positive feedback circuit like this, what are the conditions to make this circuit oscillate? Okay, there are two conditions known in something called Barkhausen or Barkhuizen. I don't know how to pronounce this name, but it's Barkhuizen or Barkhausen criterion. For oscillation, you have two conditions for oscillation to happen. Okay, so if you'd like this circuit to oscillate at a frequency omega 0, you have to have two things at this frequency. The magnitude of the loop gain has to be 1, and the phase of the loop gain has to be 0 or multiple of 360. So either 360, 2 times 360, 3 times 360, or negative 360, or so on. So at the end, it's a 0 degree. Okay, so you have to make sure that AB equals 1. As we mentioned before, when AB equals 1, that means H equals infinity, right? Because 1 minus AB should be 0, and H is A divided by 1 minus AB, so this is going to be infinity. So to have this condition, AB equals 1, that means its magnitude is 1 and the phase is 0, because 1 as a magnitude has a magnitude of 1. If you consider this as a complex number, it has a magnitude of 1 and a phase of 0. So the magnitude of AB has to be 1 and the phase has to be 0. And these two conditions are the two conditions that we use to check if a certain circuit could oscillate or not. If you cannot satisfy these two conditions, this circuit is not gonna oscillate. Okay, so the most important thing in a circuit to oscillate is to apply a Parkinson criterion by guaranteeing or by ensuring that the gain of the loop gain, on the magnitude of the loop gain, is 1, and the phase of the loop gain is 0. And this means in the frequency domain that you have two poles, one at omega 0 and one at negative omega 0. Because if you go to the S plane, so this is the S plane, and this is the real part, and this is the imaginary part. Having these two conditions means that you have in the frequency, in the H of S domain, like if you plot H of S, you will have two poles here, one at omega 0 and one at negative omega 0. If you guarantee that the two poles of the characteristic equation, which is 1 minus AB, this one here, and of course that A is a constant K and B is B of S, so this is a function of S. And if this function characteristic equation has two poles, one at omega 0 and one at negative omega 0, the whole system will oscillate. But if you have them here, if the two poles are here, the system will die out. So if you have them, if omega 0, if the two poles are here, so P1 here and P2 here, then the system will generate a signal and that signal will die over time. But if you have them exactly on the imaginary axis, then this will sustain the oscillation forever. A question: how about if we have them here? If you have them in the right side, if you have the two poles on the right side, what's going to happen in the output? So again, if you have them on the left-hand side, the oscillation will decay over time and the circuit will die out. And if you have them exactly on the imaginary axis, then this will sustain a constant oscillation. So the system will oscillate forever in a constant with a constant amplitude. How about if we move them to the right side? If we have two poles, but in the right side of the S plane,
it'll be unstable.
So what does this mean?
It'll grow without.
That's correct. Yeah, that's correct. So the oscillation will grow forever until something happens. Like it will not grow for infinity, right? And here we say, as you said, it's unstable, and we need the circuit to be unstable because oscillation means unstable. Okay, we need the circuit to be unstable because with the stability, if the circuit is stable, that means this one. Okay, we need the circuit to be unstable. Okay, so we are designing the circuit to be unstable, but the best or the perfect design is to have omega 0 exactly on the imaginary axis, which is impossible, by the way, right? Because you cannot keep the poles here. You might design the circuit on this, like having resistors and capacitors to locate omega 0 on the imaginary axis. But however, a certain a resistor has an error, or maybe it changes its value with temperature or something, or the transistor changes its beta through a temperature, then omega 0 will go here. Okay, so these two poles will slightly move to the left, then the oscillation will die out. Okay, similar to like igniting a fire, igniter or something. When you start it and it doesn't sustain the output, then it's a stable system. So you need to have something that sustains this by keeping omega 0 and minus omega, like the two poles, exactly on the imaginary axis. Something else could happen if you design that they move to the right. In this case, they will keep growing theoretically or ideally to infinity. But in reality, since these circuits are biased through a certain volt VCC and minus VEE, or VDD and minus VSS, then this oscillation will saturate at these values at the end. So they will be clipped at VCC positive and minus VEE negative. So you cannot have this forever. And as I mentioned before, this is similar to a situation when you have a speaker in a room, and you are talking in a microphone, and then there is a feedback in the room, acoustic feedback in the room, and you start hearing the whistle in the speakers. Okay, you might have seen this many times when you have a room, a large room, and you have a speaker somewhere here, and you are talking here in a microphone, and the sound goes and hit the wall and comes back to the speaker and gets amplified. Sorry, the sound goes this way, okay, and come back to the microphone and gets amplified in the amplifier and goes to the speaker and then feedback to the microphone again, and then keep amplified until you hear this whistle. That means the system has reached this point here. Okay, you have two poles on the imaginary axis, so you have an unstable system, and the amplitude is growing. But since this amplifier here is biased through a DC voltage or certain voltage, then this will be the saturation point. The output will never reach above these limits, so it will be clipped by these limits. Okay, so we need to design it in this way by placing the two poles on the imaginary axis. Okay, let me give you here an example of understanding this Parkesian criteria of oscillation. So assume you have a loop gain or a system with certain feed-forward transfer function of A1 and A2, and feedback transfer function of B1 and B2. And we need to find A2 such that this loop makes an oscillation, to guarantee that this loop will oscillate. Okay. Well, oscillation means that, don't forget this, AB should be 1. So the feed forward multiplied by the feedback should be 1. Okay. So the feed forward is A1 times A2. So A in this case is A1 times A2. And B of S is B1 times B2. We need to multiply. If you multiply all of this, this should give you 1. Okay. So if A1 was an amplifier, so this is an amplifier with a gain of 10 and a phase shift of 180 means negative 10. So this means negative 10, right? Because an angle of 180 means negative 1. So this is an amplifier, an inverting amplifier. And A2, this is what I'm trying to find, how to design it. And B1 is a gain of 1. So this is an all-pass filter with a gain of 1. But it has a phase, right? It has a phase of negative 135 degrees. And B2 might be just an attenuation circuit, like a voltage divider or something. It doesn't have any phase, doesn't provide any phase, but it has an attenuation of 100/2 or 0.02 gain. Okay. So simply we have to satisfy that AB equals 1. So AB means we multiply this by this by this by this, and you equate this with 1. Okay, so 10 times 1 times 0.02 angle. In multiplication, you multiply the amplitude, so you have to multiply the 10 by the 1 by the 0.02, and you add the angle. So you have 180 plus minus 135 plus 0. So this is the total angle. And this, you multiply this by A2, because A2 is in the loop, and equate this with 1. So if you multiply this, this is going to give you 0.2, and this is going to give you 45 degrees. I think there's a mistake here. This should be negative. So correct this. This is negative. Okay, this is negative 45 degrees. So so A1 has to be 5 and angle negative 45 degrees. Okay. So if you design A2 to be a filter with a gain of 5 and a phase response of negative 45 degrees at this frequency, at whatever frequency you are working at, because this is the gain at a certain frequency. This is not the gain as a function of omega, it's at certain omega. Okay. Can you hear me? Hello?
Yes.
Okay, because it shows the message that my internet connection is unstable. Okay, so do you have any questions? So this is how to apply the Parkesian or Barkhausen, sometimes they call it Barkhausen What do you think? What's the right pronunciation of this word or this name? Any idea?
What was that? I couldn't hear it.
What's the right? What do you think the right pronunciation of this name? Barkhausen or Barkhausen or
Barkhausen.
Barkhausen? Okay. Anyway. Okay, so this is how to apply this Barkhausen criteria to find the conditions for oscillation. The first oscillator, sinusoidal oscillator we're going to study is the Venn bridge or Wien bridge circuit. And the Wien bridge circuit, as you can see it here, consists of, as I mentioned, you have an amplifier, and this is A, okay, of S, which gives you a gain of K. So this is a constant gain K. And this, so this non-inverting amplifier, so this is non-inverting amplifier, right? Because the input is here applied to the positive terminal and the feedback on the negative terminal. So this is a non-inverting amplifier that makes the circuit A. So this is here. So this is here. All this is A of S, okay? And it is K, okay? And from this point all the way here, this is the circuit B of S. So as you can see that A of S is just a non-inverting amplifier, and the B of S is a selective filter that's band-pass filter. Why? Because this portion here is a high-pass filter, right? This is a high-pass filter. And this portion here is a low-pass filter, right? So if you have Z1 as a high-pass filter and Z2 or Z series as a high-pass filter and Z parallel as a low-pass filter, then the overall is a band-pass filter, okay? You can redraw this circuit in a different way, so just to see the feedback thing. So we can draw it this way. So this is A of S, and this is B of S, right? So as you can see here, we have the output taken from here, from the output of the operational amplifier taken from here, and then we feed it back to the negative feedback using this voltage divider, and we also feed it back from the other side to the positive terminal using this filter. So this feedback here is just to determine the gain of A of S, which is K. So this is why K has to be, so this one has K. K equals, how much is the gain here? Can you tell me? From this point to this point. Sorry, from this point, the Vn to the V out. For this block here. This is a non-inverting amplifier. What's the gain of a non-inverting amplifier? Do you remember?
So 1 plus R2 over 1.
That's correct. So it's 1 plus R2. In this case, R2 is called RY, and R1 is called RX. So this is R2. So you might find it R2 somewhere in the textbook, and this is R1, but here in this slide, it's RY and RX, okay? Okay, and the B circuit is this band-pass filter, and we have to find the transfer function of this section here, okay? So we'll study this and we'll analyze this circuit to see the conditions of oscillation. So we apply the Barkhausen criteria to see what are the conditions for this circuit to oscillate, okay? So this might be a typical question. I give you a circuit, okay, and I ask you what is the condition for this circuit to oscillate. And what you need is to analyze this circuit to find the loop gain. So the main point is to find the loop gain, to find A, to find B, and multiply A times B and equate this with 1. And from this, you find the conditions for oscillation. What's the frequency and what's the gain? Mainly how to find the gain of this amplifier and the frequency, center frequency of this bandpass filter. Okay, so this is what we're going to do now in few examples. So to analyze this, we have this circuit here. It's drawn here, redrawn here again. So if you analyze this, let's find the gain, as I mentioned, or A of S. As we mentioned, it's 1 plus Ry over Rx, and this is called K. How about B of S? Okay, B of S is the transfer function from this point to this point, right? So what's the transfer function from here to here? B of S. Okay. Well, you have here one impedance, and you have here another impedance. This is called Z series, and this is called Z parallel, right? So to find B of S is Z parallel divided by Z series plus Z parallel, right? How much is Z parallel? Z parallel is the resistor R parallel to the impedance of C, which is R parallel to 1 over SC. How much is Z series? It's R plus the impedance of C, which is R plus 1 over SC. So this is Z parallel, and this is Z parallel, and this is Z series. Okay, so this is Z parallel, this is Z series, and this is Z parallel. And if you do the math here, you will end up with this function here. So this is B of S. Okay, now we need to multiply B of S by A of S and equate this with 1. This is the Parkhesian criteria. So you multiply K by this and equate this to 1. So this is what we have. So the loop gain, so this is the loop gain, should equal 1. And if you have this and you do cross multiplication and rearrange the terms, you will get this equation here. S squared plus 3S divided by RC minus K times S divided by RC plus 1 over RC squared equals 0. Okay, and from this equation, we're going to find the conditions for oscillation. So if you have values of S, which is j omega, by the way, don't forget that S is j omega. So values of j omega or omega that makes this 0, at this value, this system will oscillate, or this circuit will oscillate. So let's see what these conditions are. Oops. So now we have this equation. I'm rewriting it again here, and we substitute S with j omega. So what we're going to have here, S squared becomes omega square, negative omega square, right? Because j square is negative 1. So this is negative omega square plus 3 j times 1 over RC. Okay, you substitute S with j omega. So this is going to be j omega over RC, and with the 3 minus K, okay, times j omega over RC plus 1 over RC whole square equals 0. You will notice that this equation here has a real part plus j imaginary part. Yes, Arwasafni, do you have a question?
Yes, I was just curious about the notation for the impedances. So is the capacitance and the resistance the same for both impedances? Just
Yes. R is the same. Yeah, you have the same resistance, the same capacitance. Yes.
okay, and this is the case for all line bridge circuits?
Yes, for the one that we are designing here, to simplify the design, we have to make the resistors are the same and the capacitors are the same. For this side here, for the filter circuit, for B of S. But for this one, no, it's not necessary to be the same, because we need to have a gain here, and we'll see how much this gain is. Because this depends on the value of K that makes this oscillate. So we are trying to find two things, okay, based on this analysis, to find how much is K and how much is omega 0, okay? So how much is K that makes, how much to choose Ry and Rx to select K, and how much is omega 0 using this selective frequency selective circuit that will make this output here. By the way, the output is here. Huh? No, this is not the output. I rearranged them just to see that we have an A of S and B of S, but the output is taken from here. And by having this K applying the condition AB equals 1, we can determine two things from here. We can determine K and we determine omega 0. That makes AB equals 1, okay? And under this condition, the output will be an oscillation. So this is the whole idea. You have a circuit, you try to determine A of S, which is, by the way, A of S all the time is not going to be a frequency selective circuit, doesn't have a capacitor here. A of S is a pure gain. It's a constant. You know, if you draw the transfer function here, it's constant. K, okay? But this one, as you're gonna see, it's a selective filter, you know, it's a bandpass filter. It has omega 0 here, okay? So we need to find this omega 0 and this K that makes this oscillate. Under what condition? By applying this condition. We find the gain A, which is K. We find B of S, which is the transfer function here, multiply them and equate this with 1. And from this equation, we can find the two, because this equation is a complex one. It has real and imaginary. And using the real and imaginary parts, we will find K and omega 0. Okay? And here we assume that R is the same and C are the same. Okay? Okay. So as you can see here, we have, where are the imaginary parts? Now we have the real part. This is a real part. And this is a real part. Okay, so together minus omega square plus 1 over RC square. This is the real part. And since everything is 0, that means this is 0 and this is 0. If you have a complex number that's 0, then the real part has to be 0 and the imaginary part has to be 0. So we equate the real part with 0 and the imaginary part with 0, and we solve for omega and K. This is the idea. So if you equate this with 0, you will find minus omega squared plus 1 over RC all square equals 0. That gives you omega 0, or this specific frequency equals 1 over RC. So the frequency of oscillation is 1 over RC. To make this happen also, you have to equate the imaginary part. The imaginary components, this one is the imaginary component and this one is the imaginary component. So if you add them together, you will have j omega over 1 over RC times 3 minus K equals 0. And you solve for this. This gives you, because omega actually is 1 over RC, as we mentioned here. So this will cancel. No, actually, yeah, not cancel. I'm sorry. So here, this is two terms, two multiplied terms, and we equate them with 0. So this is not 0 for sure. This omega times 1 over RC is omega square. And if this is not 0, then this term has to be 0 or K has to be 3. So the two conditions for oscillation is that omega 0 equals 1 over RC and K equals 3. So if you satisfy these two conditions, the Wien bridge or vein bridge circuit will oscillate. Okay. And if you do this, you are actually, as I mentioned before, you are placing the two poles of the characteristic equation. This is the real part and this is the imaginary part. You are placing the two poles on the imaginary, exactly on the imaginary axis. If you select omega as 1 over RC and K as 3, and this is going to be omega 0, which is 1 over RC, and this one here is negative omega 0, which is negative 1 over RC. But in reality or in practice, okay, practically we don't design in this circuit on the sharp edge exactly on the imaginary. We have to keep K is slightly greater than 3. So we choose K slightly greater than 3. Like for example, K equals 3.05 or 3.1 or 3.01, something just slightly above 3. Okay. You might say something, okay, if you design K greater than 3, actually you are moving these poles here to this side. So the system will start growing. The output will grow without boundaries, okay? And in reality, this is not going to happen because, again, it will grow and at a certain point, it will be clipped by something, and we're going to see this, how to design something that will clip this at the end and stop this ongoing growing. Okay, so slightly we designed the circuit with a K slightly above 3, which means that R2 over R1 has to be slightly above 2, right? Because remember that K is how much? If you remember, K is 1 plus Ry over Rx. Okay, so in this case, theoretically, we have to design Ry equals 2Rx, right? Or Ry over Rx has to be 2, right? Actually, we make it slightly above 2 a little bit, like 2.05 or 2.01 or something, okay? So that we can ensure that the oscillation will happen, because if you design it exactly at 2, for some reason Ry might be smaller a little bit than its value, then this gain will be slightly less than 2 and the signal will die out. So you have to make sure you cannot design it exactly sharp to as 2. So we intentionally design it slightly above 2 to create the oscillation, and the oscillation will grow. Okay, and then we'll see how to limit this one, how to stop this from keep growing. So let's check the condition. So this is A of S, as we said, it's K, which is 1 over 1 plus Ry over Rx. And B of S is this one here, which we did before. At omega equals 0, omega equals omega 0, A of S is not going to change. It keeps as K, which is 3. And B of S in this case, if we substitute omega here with omega 0, and remember that omega 0 is 1 over RC, if you replace every S here, so we just replace S with J omega 0, which is J over RC, right? If you substitute S with this, you're gonna end up that B of J omega 0 is 1/3 angle 0 degree. This is only at omega equals omega 0, which is correct, because if you multiply A of S by B of S 3 times, so this is 3 times 1 over 3 angle 0 degrees, and this is 1 and angle 0 degrees. Okay, so in this case, the circuit B is a selective circuit, as you can see, and it does have a value at the resonance frequency omega 0. Actually, in this case, it's F0, exactly 1/3 the gain. So if you multiply this gain by the 3, it becomes 1, and the phase shift of this one is 0, and the phase shift of this one is 0 also. So the total phase shift is going to be 0, and the total gain will be 1. So this satisfies that the criterion AB equals 1. Okay, so this is a check of oscillation condition. Another analysis, just to show you why we call it Venn bridge, why we call it bridge. Okay, we didn't see this bridge. Actually, you can redraw the circuit this way, and in this way you can see that Ry and Rx form 2 legs of the bridge, and the Zs and Zb forms the other 2 legs of the bridge. So you can redraw the circuit in a different way that shows you the non-inverting amplifier and the bandpass filter, B of S, as a bridge. So this is why we call it a bridge, okay? Because it could be drawn this way. You have an amplifier with 2 legs in each side forming a bridge, okay? And if you analyze this, as we mentioned, you will find that at omega 0, the ratio between Zs and Zb is 2, and the ratio between Ry and Rx is also 2. Okay, so it makes a balance. You know, at oscillation, the circuit is balanced and reach equilibrium, and it will sustain at the output here. It will sustain the oscillation if we design Ry over Rx to be 2 and Zs over Zb to be also 2. let's take this example to understand how to design a circuit like this. So the example says design a Venn bridge circuit to oscillate at 20 kilohertz. Okay, and we're given the circuit here. So we need to define many things here. We need to, in the design, we need to define R1, R2, C, which is the same here, and R. So we need to define R1, R2, C, and R. Okay, how to define them? So basically, we start by the two conditions. We have two equations. Omega 0 equals 1 over RC, and the other condition is that K equals 1 plus R2 in this case, R is R2 over R1, and this equals 3. Okay, so from this condition here, we can define RC as 1 over 2 pi F0, because omega 0 is 2 pi F0, and F0 is 20 kilohertz. So we define omega 0 as 2 pi times 20 times 10 to the power 3, and we solve for RC. So this is RC, okay? And since you have now 4 variables, you need to find 4 parameters or 4 variables using 2 equations. Then you have to assume certain values. You cannot find 4 values given just 2 equations. So I'll assume R is 10 ohms. Okay, maybe it's not given here, but it could be given. So I'll assume if R equals 10 ohms, then C has to be 796 picofarads. Okay, and if you use this one, you find R and C. So you found this one and this one. Okay, with this extra condition, you know, extra condition that will assume that. So this is assumed. Okay. And the second condition, we know that R2 over R1 should be 2. Then also, we may choose R2 as 20 kilo ohms and R1 as 10 kilo ohms. Okay, I'm not sure if this should be 10 kilo ohms or 10 ohm. Can you please try it, try to apply R with 10 ohms here and see with 796 and see if you get this number or not. I'm not sure if this should be kilo ohms or just 10 ohms. I'm not sure. But anyway, so to make R2 over R1 as 2, then we need to divide, if you assume R2 is 20 kilo ohms, then R1 has to be 10 kilo ohms. So this one is half this one, because you have to choose R2 twice R1 to make this ratio. Okay, so if you choose R1 as 10 kilo ohms, then R2 will be 20 kilo ohms. Okay, so based on the criteria and the assumptions, we can find the values. Any question? Okay, now we talked about if AB has 3 cases, right? We said that A times B could be less than 1, okay? And in this case, the oscillation will die out. Or could be greater than 1, and in this case, the oscillation will grow without boundaries. And the last case, if it's exactly 1, and in this case, the oscillation will be sustained with a constant amplitude. So how can we guarantee this case? We need to design for this case, but it's not easy because you are designing on the boundary and that locating the poles exactly on the imaginary axis, which is impossible to do. So should we be designing exactly at this case, or should we think about one of these things? Of course, this is impossible to design. Practically, you cannot design on a sharp value of 1 to locate the 2 poles exactly on the imaginary axis. This is not going to happen. Because if you design them this way, and for any reason, you know, for the temperature or for tolerance in the resistors on the components, then these poles might move to this side or to this side. Okay, so they come here or they come here. So definitely you cannot design them exactly on the boundaries like this. Rather than that, you cannot design this way, because if you design this way, they are not oscillating. You know, the circuit is dying and it's not going to oscillate. And definitely you have to design them this way. So you have to put them slightly here by making K slightly bigger a little bit than the design value. So if you have K as 3, then you have to make slightly, K slightly bigger than 3. So to move them slightly to the right here, okay? And in this case, you are creating this situation here, okay? And this what explains this point here. So you have the characteristic equation here, and you equate this with 0. So this is the characteristic equation. You solve, you find the poles. These are the two locations of the poles, okay? So if K is exactly 3, okay, so if K is exactly 3, what's going to happen? So K is exactly 3, then this term here is 0. So the real part is 0. You don't have any real part. And the imaginary part, this term here is also 0. And the imaginary part will be just J. So the imaginary here is just J square root of 1 over RC square, right? Which is J omega 0, right? And plus minus, right? Plus minus, plus minus. So you have one here at omega 0 and one here at negative omega 0. So this is if you design K precisely as 3. So then we have an oscillation, a continuous oscillation like this. Well, how about if you design K slightly greater than 3? If K is slightly greater than 3, then you move the two poles to the right a little bit, and the output will grow. If you design K slightly less than 3, then you send them to the left and it will die out. Okay, so definitely we design this way. This is our design. We will shift the two poles slightly to the right to make the oscillation grow. But we are not going to leave it to grow forever. We have to limit it. We have to stop this growing at a certain point. And we are going to see now how to do. And this is what we call nonlinear gain control. Why nonlinear? Because a circuit that clips, clipping circuit is a nonlinear circuit. Because the output is not a linear function of the input. It's when you clip the circuit, now you have the output like this, okay, clipped like this, then the circuit is a nonlinear. So it's called amplitude stabilization or nonlinear gain control. Okay, so this is the same thing. How to do this? There are several techniques actually of doing this. The first technique is to leave the power supply rails to limit. You know that any operational amplifier is supplied by VCC and VEE. So leave these supplies to limit to make the clipping levels. Or you can use a component in the circuit such as a transistor, a nonlinear component, and use the VBE of the transistor. VBE, we know it's 0.7. So the output will be limited between 0.7 and 0. Or you can add another component such as diodes. We'll see this now. Or a Zener diodes to clip the output at certain level. So this is an example of how to do a nonlinear gain control or to stabilize the amplitude, the growing amplitude. Is, as you can see, it's the same circuit. So this is B of S, right? And this is A of S, right? Before we had R2 and R1 only, and here was CR, CR, that's it, right? Now we add another branch parallel to R2 with R3 and two diodes, D1 and D2. And D1 and D2 are connected parallel back to back like this, okay? So what's gonna happen? Once you connect the circuit and you apply the VCC and VEE to the amplifier, then the output will start growing from a small value, right? But since the output here is very small, these two diodes are reverse biased. So they are open circuit, okay? Now, if the two diodes are open circuit at very small output values, then R3 is not included in the circuit. And the gain is calculated this way, which is going to be greater than 3. So as I said, we design R2 and R1 to be greater than 3. Okay, for example, we can design R1, for example, give you a design R1 as a 10 kilo ohms and R2 as 21 kilo ohm. So R2 over R1 is greater than 2, and 1 plus 2 is greater, 2.1, for example, is greater than 3, right? So this circuit with this gain without R3 has a higher gain, a gain higher than 3, right? So the output will start growing. Once the output grow enough to a level that becomes higher than the 0.7 of these two diodes will be on. One of them in the positive cycle, and the other one in the negative cycle. Okay, in this case, what's going to happen? Once they are on, one of them is on, so R3 will be included with parallel to R2 in the calculation of the gain. So the gain here in this case is R2 parallel to R3. And we know, of course, that R2 parallel to R3, no matter how much R3 is greater than R3. Is less than R3, right? If you have a parallel combination of two resistors, so this is going to be less than R3, right? If this is less than R3, then this whole thing is less than 2, and this is less than 3. So now you have an attenuate, a gain that's less than 3, and this doesn't make a growing. This makes a decay in the oscillation. So once you go above, slightly above the diode clipping voltages, which is 0.7, then the circuit should start decaying. But again, once it decays, the diodes will be off, and the R3 will be out, and we go back to the gain being above 3. So in the steady state, the gain will remain at 3, because if it goes above, these two diodes will conduct, and R3 will be in, and the gain will be smaller than 3. If they grow below, if the decay below the 3, below that condition k equals 3, so this will decay, then the two diodes will be off, and R3 will be disconnected, and the gain goes back to above 3. So in the steady state, it will keep the gain at 3. Do you have any question? Someone is asking, how does the non-inverting and inverting gain affects the oscillation? Okay. Okay, a good question. Do we have to have here, can we have a non-inverting gain? Like, can we have, what do you think here of this gain? Is it an inverting or non-inverting filter? So this is A of S, as we mentioned, and this is B of S. What's the gain here? I mean, this A of S, is it a non-inverting or an inverting amplifier? Any answer? Non-inverting, that's correct. So why is non-inverting? Because the signal is applied to the non-inverting terminal, and the feedback gain, or the gain is connected to the negative, the inverting loop, or the inverting terminal. So here we cannot connect this to the inverting terminal, right? I mean, this output cannot be fed back to this. So here we don't have an inverting amplifier. We have just non-inverting amplifier. Okay. So the gain here is a constant, and it is 3, a positive 3, right? And this one has a gain of the transfer function of 1 over 3. So this is a positive 1 over 3. You cannot have this as a negative. So the gain here is 1 over 3, and the gain here is 3. So the overall gain, the loop gain, is 1. So we don't have any negative signs here, okay? Another way to do this, a similar way of the clipping thing, is to use 2 diodes in this fashion here. So again, also, if we start the circuit by, once you connect the supply voltage, VCC and VEE, and due to any thermal noise inside the amplifier, it will build up an output. Output will start building up, okay? If the output is small enough not to trigger D1 and D2, then they will be open circuited. So this is open circuit, and this is open circuit. Okay, so if D1 and D2 are open circuits, then the 10K is used in the feedback gain calculation, right? So now if you assume, if you take off this one, oops, if you take off this one and you take off this one as well, the circuit will come back to the original shape like this. So this is the 10K will be here, and maybe some plus portion of this one, because this is potentiometer. You can see the 10K is series with something here, and the other portion is here. Okay, so if the input is, if the output is still small, these two diodes will be off, I mean not conducting, and the 10K will be working fully in the feedback. And if you reach a certain level that makes V output triggers D1 and D2, one in the positive cycle and one in the other cycle, because D1 and D2 are not going to be working together simultaneously. One of them will be working at the positive cycle, and the other one will be conducting in the negative cycle. So if any one of them is conducting, then you will have a short circuit, right? So R0, 10K is not added here. The only portion that's added is the portion from this potentiometer here. So you have a smaller value. So this is less than R 10K. Okay, so the gain here is smaller, and this will make this start to decay, right? So the output should theoretically start to decay. Once it decays, this will turn off again, and you insert 10K again, and you start over. So at the steady state, the output will sustain the oscillation at a constant amplitude. And I think we have a slide here. Yeah, this is how it works without. So this is without amplitude stabilization, without a nonlinear component, without having any diodes, anything. And you can see here, you see, it will grow forever. But what is going to stop this growing is the VCC, okay? And in the other side, what's going to stop the growing? Sorry. So this is the clipping due to the VCC supply, and this is the clipping due to the VEE. So this is VEE, and this is VCC. So it will grow until it will be clipped. If you can see here, I'm not sure if you see this, you know, the oscillation here stopped. You know, if you continue, this is going to continue like this, you know. Sorry. It's going to continue only only with this maximum value and this minimum value, okay? But if you install the diode clamp, this is what you're going to get, okay? So this will limit the output, not at the 15 and minus 15. It will be way below this, maybe around 0.7 or around this value, okay? So it will grow. So here we are placing the two poles to the right of the S plane, on the right of the right-hand side of the S plane, slightly on this above the real part is slightly above 0. So they will grow until they will be clipped by the two diodes. Okay, now we move to the second circuit, which is the phase shift oscillator. Sometimes you call it phase shift quadrature oscillator or phase shift oscillator. Well, this phase shift oscillator consists of, as you can see, this is A of S. Okay, so this is A of S, which is K, and this circuit here is B of S. And as you can see, how much is the gain of A of S? If you have the input here and the output here, how much is the gain of this section here?
Unity.
Unity, but
Is it just unity because of the R over R?
Yeah, unity, but it's at the -1, right? Because this is inverting now. So this is -1, right? Why? Because it's minus R over R, so it's -1. So the gain here is -1. So if A of S is -1, how much is B of S should be to ensure that AB equals 1? Remember that the condition for oscillation, AB should be 1. Okay? We know that A is -1. How much B of S should be at the oscillation frequency to guarantee that A times B equals 1?
-1.
-1, 2, right? So -1 times -1 is 1. So this guarantees this. How to create this? We have here two low pass signals, okay, or two phase shift signals. Each one has a gain of -1 over SCR, which is a 90 degree, which gives 90 degrees. So this one has a 90-degree phase shift and a gain of 1, and this one has a 90 degrees phase shift and a gain of 1. So by adding by adding these two circuits in series, you are creating a total phase shift of 180 degrees. So 180 degrees here, which is a -1, and 180 degrees here, which is a -1, gives you 360 degrees, which is 0. Okay, so angle 360 means angle 0. So this is the idea. The whole idea is to create one here with a -1, and we create a circuit here with a -1, and you have the total gain of a loop gain of 1. Okay, we can find this way, since each section here gives 1 over SCR, then with a negative, of course, because you have you have inverting here and inverting here and inverting here, so everything is negative. So -1 over SCR times -1 over SCR, so this is the gain of these two sections, and times -R over R, which is the gain of the third section, gives you this. So this is how to analyze the circuit. Again, we have to find B of S, A of S, multiply them, and equate this with 1 as the Borcasian criteria. Okay, so if you equate this, if you multiply them together and equate this with 1, and equate the real part and imaginary part, and actually here we're going to have just real part, because 1 over S square is minus omega square, and since you have a minus here, so this will cancel, because S square equals minus omega square. Then this minus will cancel, and you will have this condition omega equals 1 over RC. And how much is K? K has to be -1. So these are the two conditions for oscillation, to have K as -1 and omega as 1 over RC. But the problem with this circuit is that you cannot design this phase shifter by exactly 90 degrees, because 90 degrees is at a very specific frequency, and you cannot design this precisely to give you 90 degrees phase shift. How to solve this problem? So instead of creating two sections with 90 degrees phase shift each one, we are going to create 3 sections with 60 degrees each. Okay, so instead of creating 2 sections with each one 90 degrees like these two, we can have 3 of them, and if they are identical, then each one can have 60 degrees, 60 degrees, and 60 degrees. Okay, so the total here will be 180 degrees, and this one is 180 degrees, so the total is 360. And by the way, this is the gain, you know, this is the RR thing, you know, this is the RR thing, you know, R, and this is the inverting, and this is non-inverting connected. So this gain could be replaced, could be placed here, or could be placed here, doesn't matter. You know, you can place it at the beginning here or at the end here, doesn't matter, because the output here, the input here is and the output here, or you can switch it to the back, because we are concerned about the loop gain. Okay, so it doesn't matter if you put the gain here or at the back. Okay, so in this case we put it in the back here, or you can put it here, it doesn't matter. Okay, So every one of these makes a phase shift from 0 to 90. And by the way, you can also design this as a 45 degrees, this is 45 degrees, and this is 90 degrees. Okay, the most important thing is that the total is 180. And most likely we design them equally, 60, 60, 60, so you have 180 degrees. Okay. So this is more practical circuit than the previous one. Okay. Another way, you can see this is the same as this one, but I moved back, the gain to the front. Okay, so it doesn't make any difference. You have minus K here, okay, and you have this one. So if you analyze this circuit, and I'd like you to do this as a homework at home, okay, go ahead and find B of S, okay, by finding the transfer function from this point to this point. So this is VF, and this is VN, and this is V out. So B of S is VN over VF, right? And AS is V out over VN. And of course, this is minus K because the only thing here is minus K. And how about this one? If you do this one, you're going to get this whole thing here. S cubed, RC cubed, and so on. Okay. Now, so we found A of S, we found B of S, we apply the Cartesian condition for oscillation by multiplying A times B and equating this with 1 and solving for the real and imaginary parts. This will give us omega 0 as 1 over square root of 6 RC and K as 29. So you have to have here not 1, you have to have a 29 gain. Okay. And of course, the gain of B of S as a magnitude at omega equals omega naught should be how much? How much is the gain of this circuit at the oscillating frequency? Should be
1 over 29.
That's correct. It has to be 1 over 29. 1 over 29. That's correct. Okay. But actually not 1 over 29, negative 1 over 29, because this is negative 29 here. You have a negative 29 here. And this has to provide a number that if multiplied by this gives you 1. So this has to be minus 1 over 29. Again, this is the gain only at the resonance frequency, at the oscillating frequency. If you design this to have a gain of negative 1 over 29 at omega 0, and this one is always negative 29, then this output will oscillate at omega 0. Okay. We finish by this example quickly. So you have a circuit here, and you have R as 12 kilo ohm and C as 150 picofarads, and we need to determine the oscillation frequency. Okay. So simply we just use this one. So oscillation frequency omega 0 is 1 over square root of 6 RC, and you know the R, you know the C, then you can find omega 0. The second part is to design the circuit such that the frequency of oscillation is this, and let C be this, find R. Okay, so this is the other way around. Here I'm giving you R and C, and I'm asking for F node. And here I'm giving you F node and C, and I'm asking for R. So you use the same equation to find R. Okay, so it's a very easy one. Okay. And you remember that R2 over R1 has to be how much? Over R, sorry, has to be 29. Right? So this has to be 29. So you can design and find R and R2 as well. Right? Okay, thank you so much. Do you have any questions?
I have one about so the general form for omega is never mind.
Yeah, it doesn't have a general form, but it's a function of 1 over RC. Okay, it could be 1 over RC, 1 over 3 RC, 1 over square root of 6 RC. You know, it depends on RC. How to find it? We have to find B of S. Okay, the feedback circuit and the feed forward circuit, and multiply them and solve for this condition. and this will
Right.
give you A0, omega 0 and the K, the two conditions for oscillation.
Right.
Okay, so it differs from one circuit. Another circuit, you might find this 3, for example, or another value, but it's at the end, it's a function of 1 over RC. And again, all the capacitors are the same and all the resistors are the same.
Okay.
Okay. So next time we will study quickly the LC circuits or the LC oscillators. And if we have time, we'll go to the non-sinusoidal oscillators if we have time. Okay, and we'll finish by the next class, and the class after we will do a quick review of the questions that will be in the final exam. Okay. Thank you so much, and see you next week.